Hi, this is the demonstration of converting decimal to IEEE 754 floating. There are two standard type models, which is 32-bit single precision and 64-bit double precision, which is like more often used. And there is one more which is not standardized but still used often, which is 16-bit half precision. So let's see all the three ways of representing a decimal into these three formats. So let's start with this one. So 32-bit representation. Representing a decimal number in the form of a 32-bit IEEE 754 floating point single precision floating point representation. So to do that, we have to take a decimal number. So let's take 48.3. So it is base 10, so we need to convert it to a 32-bit floating point. So to do that, the first step is to convert the number, convert decimal to binary format. So these are the standard steps. So it doesn't really matter to which standard you're converting, so 32-bit, 64-bit or 16-bit, because it's all about the representation. So let's start with this. So first I'll convert. So here, if you see the decimal number which I have taken, it's 48.3. So basically it has the fraction part and the decimal part. So the conversion is, we have to do the two set of conversion. So first, sorry. So first let's convert 48, which is in decimal, to binary. The process is by dividing it by 2, because binary can represent 1 and 0. So just 2 bits, right? So basically we have to divide 48 by 2. 2 2s are 2, 4s are 8, remainder is 0. 2 2s are 4, the remainder is 0. 2 6 are 12, remainder is 0. 2 3s are 6, remainder is 0. 2 1s are 2, the remainder is 1. So this is the binary representation of 48. So 48 in decimal is equal to, we have to start from here. So bottom up approach. So 1 1 0 0 0 0 is the binary representation. So it can be also written as 2. So now, so the remaining is the fraction part, which is 0.3. So the process is a little different. So as you can see, for the left part, so for the 48 we divided it by 2. For the fraction part, we'll be multiplying it by 2. So 0.3. So we'll be multiplying the instance by 2. We'll get 3 2s are 6, so 0.6, and we know that the remainder is 0 here. So the next time, once we are done with this, so basically this 0 is nothing but this one. So yeah, so next we have to take 0.6 into 2. So I just took this number and multiplied it by 2. So 6 to the 12, so which is 1.2. So once I get a binary high here, which is 1, so I'll take that 1 outside, and for the next multiplication I don't use this one, so it will be just 0.2. So basically the same number without considering 1, because 1 I took it outside for the representation purpose, into 2. So 0.2 is into 2 is 0.4. So the this bit is 0, so I'll just write 0. So I'll just continue the process. Here again 0. Then I'll take 0.8 out into 2. 8 to the 16, 1.6. Again I'll take 1 because there is 1, and I'll take the remaining, which is 0.6 into 2, which is 1.2. So again 1, so I'll take this out. So now if we see, we can see that 0.6 into 2 is 1.2, and we took 1 outside, and the same instance is repeating here, which means from here onwards this whole sequence is gonna repeat. So when we get to know this, we can stop the process and we can consider the number directly. So the number now will be, we have to take from the top, which is 0 1 0 0 1. So which is this 0 1 0 0 1. After that the sequence is repeating. So the sequence is repeating from here, right? So basically this sequence is being repeated, so we just have to take it 1 0 0 1, and we have it again, and it keeps on going. So just dot dot dot. So now we have the decimal conversion of 48 in binary and the decimal conversion of 0.3, the fraction part, in binary. So when you put together for 48.3, so 48.3, which is in decimal, now in binary it will be 11110000. So 110000. Yeah, so you should not put brackets there. So dot, we have this 0100110011, and it goes on. So we ended up with this. So the first part, which is converting from decimal to binary is done. So we are done with the part 1, which is converting from decimal to binary. The second part is converting from binary to scientific notation. So for that, we have to keep track of this. So basically, in this representation, we will be bringing this number all till here. So we'll change the color. So basically, we have to get this by hopping all the way till here. So basically, it's 1 hop, 2 hop, 3 hop, 4 hop, 5 hop. So it will be, which is, so there is 1. So 1.100000. I'm done with this, and the rest 0 1 0 0 1 1 0 0 1 1 dot 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 into 2 to the power of y2, because it's binary, and 2 to the power of the number of bits we came. So here it is 1 2 3 4 5. So this is the scientific notation. So first we converted from the decimal to binary. After we converted it to binary, we converted it into scientific notation. So now the step 3. Step 3 is converting from scientific notation to IEEE standard. So in this example, we started with 32-bit floating, right? So we'll take the 32-bit standard. So if you see here, the 32-bit standard basically has 1 bit. Oh yeah, I missed something. So it's called, the second division is exponent, and the third one is mantissa. So we'll see what are those. So for 32-bit, we have 1 bit for sign bit, and we have 8 bits for exponent, for exponent, and 23 bit for mantissa representation. Yeah, so let's start. So the first bit basically says whether the number is binary. So here the first bit basically says whether the number is positive or negative. So in this case, the number which we took was 48, so it was a positive number, so it will be 0. So it's the same thing. In general binary, we have 1 for representing a negative number, and the first, so basically the MSB says whether the number is negative or positive. So if it is 0, it means the number is positive, and if it is 1, it says the number is negative. So here the number is 48, which is like plus 48, right? So we are taking that bit as 0, and this is done. Yeah, so exponent here is nothing but this exponent. So we can see 2 to the power of 5, right? So the exponent is 5 here. So to represent the exponent, so this exponent can be basically negative or positive number again, right? So it could be like the power to maybe -5, -10, it could be anything. So basically to represent the negative and positive in the binary format, so there is something called as exponent bias. Exponent bias, which is set to 127. So now if the number is positive, we're gonna add to the exponent bias, so which will be like 127 plus 5. And if the number is -5, then we are gonna negate it from 127. So 127 is like the middle, so it represents the middle bias. So if the number is positive, add it to the 127, and if the number is negative, then negate it from 127, and then represent it in 8-bit binary format. So here so it will be, so here it will be 127 plus 5, right, which is 132. Now we are gonna do the very same procedure what we did here. After doing that, we will get the number as 1000100. So this is nothing but the binary representation of 132. The next one is the mantissa. Mantissa is nothing but the remaining part actually, which is, as you can see here, it starts from there. So this we have to ignore, we have to consider from here. Yeah, so it will be 100000100110011, and basically it repeats, right? So just put dots. So now putting it all together, since we said it's a 32-bit format, right? So to make it a 32-bit, yeah, we took 32-bit as the reference. So yeah, so now putting it all together, we will start with the sign. So basically, we'll start with, yeah, sign, and here we are gonna, let's group it with 4. So 0, so 1 2 3 4, so this 4, 1 2 3 4, so this is one set, 1 2 3 4, 1 2 3 4. Then we have this repeating groups. Okay, so sorry, so let's start representing it in 32-bit format. So 0 1 0 0, I'm done with this. I'll leave a space. 0 0 1 0, I'll leave a space. Then I'll just continue. Yeah, now it's all repeating bits. So 7, and there is one more. So there is one more, I'll write down. So 0 0 1 1. So this is nothing but the 32-bit representation of single precision number. So recapping quickly. So first we took the decimal number and we converted it to, just change the color. Yeah, so first we took the decimal number here and we converted it to binary format. So to convert it into binary format, first we had to take the decimal part and then the fraction part. For the decimal part, we'll be dividing it by 2, and we got this. And for the fraction part, we're going to multiply it by 2. And here, if there is 1, we're going to take it as 1 here, and just the remaining things we are going to take it here and multiply it by 2. And if it is 0, then just take the 0 here and take the whole number here, then keep continuing until either you get 0 here, or if the pattern is repeating. So once the pattern is repeating, you can stop it. So this was the output of the final step, the representation of binary of this decimal number. Then converting the binary to the scientific notation. So this is just bringing the points to the first place and then just powering the 2 by how much ever the points we came towards left. So once we are done with that, the next step is converting it to the IEEE standard. So for that, we have to see whether the number which we took was positive or negative. Since it is a positive number, the sign bit will be 1. And then in the 32-bit format, we have basically 3 segments, right? So one is the sign, the second one is the exponent, and the third one is mantissa. So in the exponent, it's an 8-bit one. So we have an exponent bias called 127. So this is the middle part. So if the, now we have to consider the power because it's exponent which directly represents the power. So since it is positive number, we are going to add it to 127, and if it is a negative number, we're going to subtract it from 127. So here it's positive, so we added it with 127, so we got 132. So, and we did the same conversion process to binary, and we got this number, so which is 100000100. And then the next process is to write the mantissa. So mantissa is nothing but this number, the whole number, sorry, without considering 2. So this whole sequence is mantissa, so we represented that mantissa. Then putting it all together, so we grouped in the form of 4 bits. So totally it's a 32-bit representation of IEEE format. So for the 64 and for the 16-bit, I'll make one more different video, and also for the conversion of IEEE format into decimal, so I'll make it as another part of the video. Thank you.